Guys, in this video, we are going to talk about thermal breakdown in insulators, and then we will solve an example how we can determine the heat being generated in an insulator. So let's start. Let's suppose we have an insulator. For example, we have an insulator, okay, and we connect with an external voltage source. So, for example, like in real applications, one terminal or one side of the insulator is at ground potential and the other side of the insulator is at high potential. Okay. Then electric field will be produced from high potential to the low potential or from high potential to the ground. As there is an electric field, some small current will try to flow from high voltage to the ground. So if there is an electric field, so there will be a small leakage current, and if electric field gets stronger, this leakage current will increase, and this leakage current, or we can also call it conductivity, will cause heat being produced in the insulator. Okay, as heat will be produced, this heat will further enhance the leakage current or conductivity, and this will further increase heat. This will further increase more heat, and this will lead to increase in dissipation factor. Tan delta. Okay, so the heat being produced in an insulator upon application of high voltage will depend upon the conductivity, will depend upon the dissipation factor, and will depend upon the electric field. So for DC voltage applied, the heat being produced is equal to square of electric field RMS value multiplied by the conductivity. And for AC applied voltage, heat being produced equal to square of RMS value of electric field, frequency of our AC voltage supply, relative permittivity of the insulating material, dissipation factor, tangent of delta, where delta is loss angle of the insulator, divided by a constant 1.8 into 10 raised to the power 12. And its unit are watt per centimeter cube. And in order to hold this unit, electric field in this equation must be in volts per centimeter. So using these equations, now we will solve an example. In this example, we are given an insulator which is composed of two parallel connected plane insulators, and their plate area is 0.2 decimeter square, and two materials have relative permittivities as 4 and 2.7, and their loss angles, dissipation angles, are 4.6 and 5.7, and electrode distance is 3 mm, the distance between the high voltage and the ground electrodes. If insulator operates at an applied voltage of 20 kV at 50 Hz, which of the two materials will suffer from thermal breakdown earlier? So now let's draw the geometry. The given geometry is like this. Here we have HV here, for example, and here we have ground, and the electrode distance is D is equal to 3 millimeter, or this is equal to 0.3 centimeters, and the voltage applied is 20 kV, okay, which will be the voltage across the both insulators. And now we have permittivity of one insulator as epsilon R1 is equal to 4, and its loss angle is, or dissipation angle is 4.6 degrees. For material 2, epsilon R2 is equal to 2.7 degrees, 2.7, and loss angle delta 2 is equal to 5.7 degrees. Now how much will be the, okay, let me shade this. Okay, this is my material 1, and this is my material 2. Okay, now how much will be the electric field? So electric field from high potential to the low potential will be, E in this case will be equal to U by D, gap distance, and the voltage applied, RMS voltage applied. We are interested in RMS electric field, as in the formula we have RMS. So here we will take RMS value. Already our given values are RMS, so we will use the same, which is 20 kV divided by the gap distance, which is 0.3 centimeters, which will give us the electric field equal to 6.67 into 10 raised to the power 4 volts per centimeter. Okay. So we will have same electric field in both of the material, because the um, gap distance is equal and the applied voltage across both the insulator is also equal. So E1 will be equal to E2. Now in the question, we need to determine which of the two materials will suffer from thermal breakdown earlier. So the material in which the heat being produced under these conditions will be higher, that will suffer from thermal breakdown earlier if the cooling is not efficient. Generally, our insulator can break down if cooling is less than the heat being produced. if the rate of cooling is less than the rate of heat being produced in the insulator, then insulator will suffer through thermal breakdown. Okay, so now let's solve for insulator layer 1 and for insulator layer 2. Okay. Again, the given data, we have E1 is equal to 6.67 into 10 raised to the power 4 volts per centimeter. E2 will also be equal to 6.67 into 10 raised to the power 4 volts per centimeter. And epsilon R1 is equal to 4. Delta 1 is equal to 4.6 degrees. And for layer 2, epsilon R2 is equal to 2.7 and delta 2 is equal to 5.7 degrees. And frequency of operation is given as 50 hertz. So for both cases, frequency will be 50 hertz. Okay, so we got almost all the ingredients to determine the heat being produced. So we will calculate W1 heat produced in the insulator layer 1. Again, the equation is ERMS square frequency epsilon R indent delta divided by 1.8 into 10 raised to the power 12. So we will plug all these values. We will plug all these values here and we will get W1 equals to approximately 39.7 milliwatt per centimeter cube. Okay. Similarly, for material 2, we will use the same expression but we will use these values given above. So we will get W2 equals to 33.9 milliwatt per centimeter cube. Okay, so which clearly shows that the heat being produced in material 1 is higher. So there is a possibility that material 1 will suffer from breakdown earlier. So material 1 may suffer from breakdown earlier. Okay. That's all. Thank you.